So with number 18, we are asked why magnesium has a larger radius than aluminum. They're in the same period. And so magnesium has one fewer proton than aluminum. So aluminum has a greater effective nuclear charge. So aluminum has a greater effective nuclear charge, which will make the aluminum atom smaller than the magnesium atom. That is best summed up in answer choice C. Number 19. We are given a skeleton redox reaction and asked to identify the oxidizing agent and the reducing agent respectively. So first thing I have to say is that they both must be chemical reactants. And so anything that has a product is going to be wrong. So you can quickly eliminate C and D. Chromium has an oxidation state of +6 in reactants and +3 in products. And so this is being reduced, so it's the oxidizing agent. You could also rationalize this by the fact that dichromate has a plethora of oxygen atoms. In either case, the best answer is going to be B. Sodium dichromate is the oxidizing agent, whereas hydrogen is the reducing agent. Number 20. We want the net ionic equation when we add HF and NaOH. So HF does not ionize well. And so in the net ionic equation, we will not show it ionizing well. Sodium hydroxide, on the other hand, does. And so we will show its ionization. Whenever HF does ionize, although it happens very, very rarely, you will immediately produce a molecule of water in the liquid state and a fluoride ion. And of course, you'll have the sodium counter ion. Well, these spectator ions, the sodium ions, will cancel, and we're left with the net ionic equation of the weak acid plus OH minus yields H2O plus F minus. This is best summed up in answer choice B. Number 21. We have the Haber process. Of course, this is what Haber won the Nobel Prize for his industrial synthesis of ammonia. And we are given that we have 0.25 moles of nitrogen and 0.3 moles of hydrogen. And we want to know what reagent will be left over and how much of it we will have. Let's start with the hydrogen, because for every 3 moles of hydrogen, you only need 1 mole of nitrogen. So if I have 0.3 moles of hydrogen, I will only need 0.1 mole of nitrogen. And I have 0.25 moles of nitrogen. That means nitrogen will be left over, and I'll have 0.15 moles of it. That is best summed up in answer choice B. Credited answer for 21 is B. '22, I have 3 flasks. looks more like a beaker. That's pretty sad, actually. And I have molecules kind of everywhere in 1. A little bit more concentrated in 2. And very concentrated in 3. Fewer IMFs are going to mean gas, so this has the highest entropy. Then the middle one is kind of intermediate in entropy, and then the one with the smallest entropy is going to be the third. So the best answer is going to be C, 1 to 2 to 3. Number 23. Ionic salts with the highest melting point. So we have CSI, we have NaF, we have MgO, we have ALN. And I'm going to turn this into a question that it isn't, just to give you something more complete. Let's arrange these in order of decreasing melting point. First thing, we want to look at our ions and charges. +1, -1. If we take the absolute value of the product of these charges, we get a value of 1. Sodium +1, -1. We'll also get a value of 1. Magnesium and oxide +2 and -2. So the product will be 4. Aluminum and nitride, the product will be 9. So that means aluminum nitride, and the reason we do it this way is because the charge has a greater impact than does the spacing between the ions. So we know that aluminum nitride has a greater melting point than magnesium oxide, and magnesium oxide has a greater melting point than both NaF and CSI. Now, size also matters. Sodium is smaller than cesium, fluoride is smaller than iodide. These will get closer together to fatties can't slow dance, and so NaF will have the next highest melting point, followed by CSI. So highest to lowest. Number 24. Which of the following wavelengths of light is the greatest in energy? Remember that delta E is equal to hc over lambda. So the greatest energy is associated with the shortest wavelength. Increasing energy, higher frequency, shorter wavelength. Lower energy, lower frequency, longer wavelength. So the shortest wavelength is A, which is the credited response for number 24. Number 25. We are going to dilute our cells by the same factor. Of course, to answer this, we need Nernst equation. So E cell equals E cell standard state minus 0.0592 over N base 10 log the concentration of zinc plus over the concentration of Cu plus. If I dilute them both by the same value, the ratio is going to be the same. There will be no change, and E cell will equal E cell standard state. And so the best answer for number 25 will be C. I think we can fit one more on this page. Number 26. We want to find out what mass of a metal will be deposited at the cathode. The relevant reduction chemistry that's taking place at the cathode is chromium 3 plus 3 electrons yields chromium metal. And this is going to occur for 1 hour, so that's 3,600 seconds. At a current of 3.52 amps, which is 3.52 coulombs per second. We know that a Faraday, we have 96,485 coulombs for every mole of electrons, and it takes 3 moles of electrons to produce 1 mole of chromium, and 1 mole of chromium is 52 grams of chromium. So now we have everything in place. Just to show you, all our units will cancel. And it's off to the plug and chug game on the calculator. So 3,600 times 3.52 times 52 divided by 3 divided by 96,485. I get an answer of 2.28 grams of chromium. Which corresponds to choice B. So number 26, the best answer is B. All right, so on to 27. If you guys were paying attention in lab this year, this one should have been fairly straightforward. We have a titration curve. So we are graphing pH as a function of titrant volume. And of course, titrant volume is in milliliters. So we have an initial dip, then it buffers, and then it drops. And the equivalence point pH appears to be between 5 and 6. That tells us 2 things. Number 1, this starts alkaline, so we are titrating a base. So we can effectively eliminate A from our responses. We can also eliminate B from our responses. If we were titrating a weak base with a weak acid, we'd need to know more information. We know it must be a strong acid, and in fact the acid we used with this data, and this was data that one of you guys collected in lab this semester, was hydrochloric acid. So it's a weak base titrated with a strong acid. A lot of you guys got this one right, which is good. That is credited response C. So C is the correct answer for number 27. On to number 28. If I increase the pH from 7.88, or excuse me, I'm decreasing the pH to 4.88, the hydronium ion is going up by a factor of 10 to the third, not by a factor of 3. When pH goes down, hydronium ion goes up because pH is the negative log of hydronium ion, which means that hydronium ion concentration is equal to 10 to the minus pH. When the pH goes down, this becomes less negative and H plus goes up. Number 28, the best answer is C. Moving on to 29. What is the solubility product constant for barium fluoride? Barium fluoride is BaF2 solid yields Ba2 plus aqueous plus 2F minus aqueous. If this is X, and this is 2X, the KSP is the concentration of barium to the first power, which means we can get rid of A, and that's about it, times the concentration of fluoride, not 2-fluoride, squared. So we can get rid of C, we can get rid of D. The best answer will be credited response B. Let's fit number 30 onto this one. This is a really good weak solubility equilibrium question. We have a saturated solution of magnesium fluoride. So we have magnesium fluoride, solid, that has dissociated as much magnesium ion that water can solvate and as much fluoride ion as water can solvate. And to this we're going to add HCl, which is going to be H+. The H+ will be taken up by the fluoride to make HF. HF is a weak acid. It does not dissociate well. So the overall effect is I'm going to decrease F-, and Le Chatelier's principle says we should skew or shift the equilibrium to the right, which means more will dissolve. So looking at the answer choices, A is wrong because HF is not a strong acid. D is wrong because there certainly is an effect. Now, a case where there would not be effect is if we made an acid that was a strong acid. So if we had magnesium bromide, there would be no effect because HBr is a strong acid, and as soon as we take up bromide, we dissociate it again. But HF is different. It is a weak acid. C is also wrong because it states that less magnesium fluoride would dissolve. The best answer for number 30 is choice B. All right, if we look at number 31, we have an endothermic reaction, and we want to compare the energy of activation of the forward reaction to the energy of activation of the reverse reaction. As this diagram clearly shows, the energy of activation of the forward reaction is greater than the energy of activation of the reverse reaction. This should really make sense because in an endothermic reaction, usually the reverse reaction is typically favored, and as we can see here, it has a smaller energy of activation. Best answer for number 31 is going to be choice B. Number 32. This is a really good use of the Arrhenius equation. So we're going to do log of K2 over K1 equals, so this will equal EA over R 1 over T2 minus 1 over T1. And actually, there should be a negative here, so if you want to make this a positive, you can change your signs right here. The rate constant should double, so this will be the log of 2 times R, which is 8.3145 joules per mole Kelvin, divided by 330 to the minus 1 minus 340 to the minus 1. That's really how I would input it in my calculator. And once we begin putting in values, I get an answer of 64662.8 joules per mole. Remember, we have Kelvin in the denominator right here. That is 64.7 kjoules per mole. And that matches up very nicely with A. So A is the credited response for number 32. Let's crank out a couple more here before we finish up this particular screencast. So moving on to number 33. 33 is a simple ratio and proportion problem. So you know that 28 kjoules of energy are absorbed. This is an endothermic reaction for every mole of ozone. And we need to find out how much is absorbed for 16 grams. Well, 16 is 1/3 of 48. 48 is the molar mass of ozone. So I'm just going to place this over 1/3. And we're going to get 1/3 times 28 kjoules equals 16 grams of ozone. And that's 9.33. Because this is endothermic, that is positive. And this agrees quite nicely with answer choice A. Number 34. Again, we see an application of the third form of Hess's law. We have molecular iodine and 3 moles of molecular chlorine produce 2 moles of ICl3. So we're going to break an iodine-iodine bond. We're going to break 3 chlorine-chlorine bonds. And we're going to make 6 iodine-chlorine bonds. So remember, delta H is the bond energy of the broken bonds minus the bond energy of the made bonds. So just using the data that we have 151 plus 3 times 242 minus 6 times 208. When we simplify this, we get 151 plus 726 minus 1248. So that's 877 minus 1248, which is equal to negative 371 kjoules per mole. This is answer choice D. So number 34, the credited response is D. Number 35, this question had 2 answers that repeated, both of which were correct. We want to find CS2 plus 3O2 yields CO2 plus 2SO2. And here's the data that we're given. We're given C plus O2 yields CO2, and that is defined as H1. Number 2, we have solid elemental sulfur plus O2 yields SO2, and that is defined as H2. Finally, we have C plus 2S yields CS2, and that is H3. Literally, this is how I would approach the problem. Number one, we need CS2 as a reactant. It's only present in equation 3, but it's a product. So let's flip equation 3, which means we flip the sign of H3. So that would be CS2 yields C plus 2S, and that is minus H3. I also need two SO2s as a product. So let's multiply equation 2 by 2, which means we multiply H2 by 2. So we have 2S plus 2O2 yields 2SO2. This will be plus H2. Finally, I don't need carbon or sulfur in this equation. And so we can cancel out the sulfur, because if it's a product and if it's a reactant, you got the same amounts like any mathematical equation, they drop out. But it looks to me like we need equation 1 just as it is, because I need 1 mole of CO2, I need another oxygen, I need to get rid of the carbon. So C plus O2 yields CO2. Now the carbons cancel. Of course, this is simply going to be H1. We need 2 H2s because we multiplied that by 2. And notice we have the CS2. We have the 3 O2. We have the CO2. And we have the 2 SO2. Perfect. That means that the delta H will be H1 plus 2H2 minus H3. Both B and D are represented with this result. So either B or D work fine. Now I'm going to do 36 just because I've got a little space left, and I'm going to conclude this screencast. So number 36. Actually, I'll do 36 and 37. Again, we have the Haber process. Of course, these are all gases. And so 36 says, using only chemical logic and assuming the above reaction is spontaneous, what conclusions can we make regarding entropy and enthalpy? Well, entropy is easy. We go from 4 moles of gas to 2 moles of gas. Delta S must decrease. Now this is the delta S of the system. Now that's not a driving force. So I must have the energy lowering, which means the delta S of the surroundings goes up. And the only way for a reaction to be spontaneous is if that the total entropy in the universe increases. So there must be a larger increase in delta S of the surroundings than there is a decrease in the delta S of the system. So the entropy and the enthalpy both decrease, and that is consistent with D, which is the credited response for 36. And finally 37, and we'll wrap this one up. What reactions would result in a max yield? Well, if entropy is going down, I want a very low temperature. Because if I use a high temperature, it's going to favor the side with more entropy, and that's going to be reactants. Also, if I use high pressure, it will favor the side with the least number of moles of gas. Le Chatelier's principle. And so if I increase the pressure, it favors the side with the least moles of gas, which will be products. If I lower the temperature, it's going to disfavor the side with the largest number. It'll still go to products. Low temp, high pressure. This is what won Haber his Nobel Prize. So I'm going to stop this screencast and I'll do one final one that will finish up the mock test solutions.